Good to see you all. Good morning, quantum enthusiasts and geometry enthusiasts. It's a good day to be enthusiastic because we're going to do geometry today. If you remember way back when, to the previous lecture, we learned the following things, or we saw the following things. We decided we'd stop writing all these phrases like so much amplitude here and so much amplitude here and just stack all the amplitudes into a list, a vertical list, also known as a vector. So we saw that any state of n qubits can be thought of as a vector in 2 to the power of n dimensions of unit length, of length 1. Okay? And this is hard to visualize in any number of qubits that's bigger than 1, so we'll talk some more about just 1 qubit, which takes place in 2 dimensions. And then we know that any quantum transformation, any quantum instruction, if you will, manipulates the state of the qubits or changes the vectors. And we saw that this is a linear transformation in the sense of linear algebra. Like if you apply it to the sum of 2 vectors, then you get out the sum of the 2 applications. And this is another fact that I want to tell you about today, which is that any unitary linear transformation, any linear transformation that doesn't change lengths is nothing more than a rotation or a reflection. And in that sense, like all the quantum programming you ever do, all the instructions are just rotating and reflecting a vector, which is this state. So everything is just some rotations and reflections. So let's talk about why that is, and we'll learn some things along the way. So, and actually, this was sort of already on the homework, but we'll go over it as well. Okay, so recall the definition of unitary. Unitary means that it's a linear transformation that doesn't change lengths. But that doesn't necessarily obviously mean that like it has to be a rotation or a reflection. But let's see why it does. So in fact, the first thing I want to convince you of is that once you know this unitary transformation doesn't change lengths, that also implies that it doesn't change angles. And let me try to justify that for you by physical intuition. I guess like if you read the homework solutions, maybe you'll see it justified more by like mathematics. But here's how I like to think about it. So let's say you have some unit length vector, like this red vector here. Okay, and we'll call this, we'll call this ket v. Remember this notation from last time? This just means it's a vector, a column vector, and we decided to name it v. So this is v. And let's say we have some second unit vector. I'll call it w. And I don't know, I'll make it like this one here, w. Okay, ket w. Okay, so here we have this like picture of like v and w, and they're sitting here like this. Now, this unitary transformation, it moves each one of them. It shifts it to like some other vector, and shifts the red one to some other vector, and the green one to some other vector. And the one thing we know so far, if it's unitary, is that it doesn't change their lengths. And that makes sense. These are like rigid markers. They're not going to like change their length. But maybe it could change their angle. So let's see. So maybe this is the original vectors, and maybe over here, the red one gets moved to, I don't know, here. Let's say it gets moved to, well, let's say it gets moved to straight up by coincidence. So this new vector is u, let's say a unitary u. This gets moved to like u applied to v. And it's a unit vector. And then this one gets moved somewhere else to u applied to w. And let's try to imagine hypothetically that the angle between them changes. And then we'll see that that's actually impossible. So let's say they're pretty close here. So let's say they somehow move. And now u applied to w is over here. So it's also a unit length vector. And what I want to say is like that's impossible, that it started out like this and ended up like this. And the reason is, think about the vector that like goes between the 2 tips. Okay, it's this long, but it also gets transformed by u, and its length also doesn't change. But you see, okay, if they move like this, but when they get wider, then the length vector between their tips would get longer. Or if like when they got transformed into the u world and they got like closer, then the vector between their tips would get shorter. But u is not supposed to change any lengths. So like the only way it can happen is if they stay at the exact same angle. They can get reflected, but they have to stay at the same angle. Okay, so actually what I'm saying there, and here I did secretly rely on one other property of u, not that just that it's unitary. I relied on another property of u, because I looked at this vector here. Okay, this vector is w minus v. That's how vector subtraction works. And what I claim is that this black vector, I didn't put its tail at the origin, but I claim that this black vector, when you apply u to it, you get to this black vector. I claim that this is u applied to w minus v. And why is that? Well, what it clearly is it's uw minus uv. That's what this black vector really is. But because u is a linear transformation, these two things are equal. That's basically the definition of being a linear transformation. Okay, so not only does it fix the length of these two vectors, it has to fix the length of the vector connecting their tips, and then it's pretty clear that it has to preserve their angle. So this angle change is impossible. Okay. And in particular, that means, let's say, like in 2 dimensions, you have to take the linear transformation. It has to take, like, let's say, the standard basis vectors. It has to take them to some 2 other vectors that are at 90 degrees. And that's basically the definition of being a rotation or a reflection. I mean, and similarly, like in 3 dimensions, if you take 3 unit vectors, the standard unit vectors, any unitary linear transformation has to preserve the fact that they're unit vectors at 90 degrees from each other, so they have to go to some other basis. And this is pretty much the definition of a 3D rotation. Okay, so in general, as soon as we know that it's unitary, we know that it maps like any orthonormal basis to another orthonormal basis. Now, actually, since we're going to be talking about more than one qubit eventually, we're going to have to start thinking about how unitary transformations work in higher dimensions. That's hard to visualize. So in fact, let's step up just 1 dimension and think a little bit about 3-dimensional rotations. That doesn't really correspond to any number of qubits, but it's still a valid dimension. And let's think about what it means to be, let's say, a rotation in 3 dimensions. And I have a visual aid for this. I was going to bring in a globe, but instead I brought in a basketball. So we can look at this basketball and imagine rotating it. Yeah, stay. Rotations in 2 dimensions are pretty easy to understand, right? They're basically defined by an angle. That's it. So defined by one real angle. But in 3 dimension, it might seem like much more complicated. Like you could have all sorts of crazy rotations in 3 dimensions if you just look at that basketball and imagine how it could move. But actually, the cool thing is, no. It turns out the most complicated rotation in any number of dimensions is a 2-dimensional rotation. So rotations somehow don't get that much, in some sense, don't get more complex as you go above 2 dimensions, which is nice because we can understand 2 dimensions. There's this Swiss person called Euler, and he had a theorem about this very fact, which is that, I'll say this first. It's like there are no inherently 3-dimensional rotations. That's how you can maybe think about it. Maybe more precisely, well, what this really means is every 3D rotation is a 2D rotation about some axis. Or maybe let's say in a 2D plane. Usually it's phrased as like, for every 3D rotation, there's an axis of rotation. And what does this mean? It means like, okay, the only thing we really know about like unitary transformations in 3 dimensions is like they don't change the length of vectors, right? So if you imagine the origin is at the center of this basketball and all the points on the basketball are at distance 1 from the origin, if you do a transformation, a unitary transformation, like the ball has to go on top of itself. So you might think there's like lots of different rotations you can do. Like you can do this. Actually, though, if you tried to like do it in your mind, like change the basketball's orientation, you feel like you end up just like doing some kind of 2D rotation, you know? And you might say like, oh, I can do this rotation and then this rotation. But if I do like this rotation and this rotation, is it just the same as like this rotation? And the answer is yes. I'm not sure how easy it is to visualize, but like there's no rotation you can do that's not just like a 2D rotation with some axis. I don't know. Can anybody like truly visualize why this is true? I'm not sure I can, but it's true. Maybe you'll prove it on your homework. Yeah. Does anybody want to hold the basketball and try it? You can manipulate it with your hands. No? Oh, yeah? Uh-oh. No, I'm not going to do it and kill this person in front of you. Great. Yeah, try to do a genuinely three-dimensional rotation. I dare you. I dare you to defy Euler. Okay, so yeah, in your homework you'll learn to justify this, I think. And this fact like generalizes to higher dimensions. So now I'm going to tell you like a very important theorem for us. You may or may not prove this one in your homework. We're going to technically never rely on this theorem being true, but it'll heavily motivate a lot of the things we'll do. So this is kind of a good fact to know. And it's about rotations in any dimension. So let me write it here. So this is like more general than Euler. This is a long theorem. So let's suppose that U is a real, I don't want to talk about complex numbers, unitary transformation in d dimensions. Okay, so it's some kind of transformation that maps the d-dimensional basketball back to itself and doesn't change any lengths and also doesn't change any angles. Then basically the short form is it's equal to a bunch of 2D rotations in planes that are perpendicular to each other. So then there are some, in fact they're unique, some perpendicular to each other. This is hard to visualize because we can't really have perpendicular 2D planes in real life, but you can have them as soon as you get to 4 dimensions. Two-dimensional planes, which I'll call P1 through PR. R will be like the number of these planes, so R is at least 0. And associated angles, which I'll call theta. It's a popular name for an angle. Theta 1 through theta r. And these are numbers between 0 and 360 degrees exclusive. In particular, they're not 0 or 360. And they're also not 180 degrees. That's excluded. Such that U does like rotation by theta j, rotation by theta j in plane pj. Moreover, you might notice that like, okay, we're in some d dimensions. You can imagine d is 3. If we have these like two-dimensional planes, 3 is an odd number, so like if they're perpendicular, like you cannot have like a sum of 2's that adds up to 3. So there may be some like leftover dimensions that are like perpendicular to these planes, or some leftover axes. And U has to act even more simply in these dimensions. So in each of the remaining dimensions, which is d minus 2r dimensions. I'll do some examples in a minute. U either does negation, it just negates vectors, or nothing. It literally doesn't change vectors. And in some sense, we're going to eventually associate doing negation with like theta being 180 degrees. Because rotating by 180 degrees is kind of like just negating vectors. And we're going to eventually kind of associate doing nothing with like theta equals 0, because rotating by 0 degrees is also like doing nothing. So in that sense, like for every possible angle between 0 and not 359, but like strictly less than 360, something is associated, either like a normal rotation or negation or nothing. Okay, so this is kind of a complicated statement. I'll illustrate with some examples, and maybe you'll see it illustrated some more in the homework. The real reason this is true, by the way, this is a fact about rotation in space. The real reason this is true is eigenvectors and complex numbers. Like the most compelling proof of this fact involves both those facts, or both those concepts.